Good afternoon. I'm Jorge Esparza, Research Fellow at the Emerging Technologies Institute at the National Defense Industrial Association. On behalf of Arun Sarafin, the Executive Director of ATI, I want to thank all attendees for your support of NDIA and ETI, and for joining us today for today's webinar. This webinar is part of our Tech 101 series, where we present complex technological concepts as introductory webinars with a focus on their national security implications. Today's episode will be covering power beaming with a presentation by Tom Nugent. Power beaming uses high-intensity light generated by a laser transmitter to transfer power wirelessly at great distances. It delivers safe, clean, and reliable persistent power even in the most austere environments. It is an emerging technology that could reshape how we generate and distribute energy and how our systems are employed. Could this technology be a game changer as we wrestle with the complexity of a potential future contested logistics environment? We will delve into this question and your own questions during today's webinar. Now, some admin notes. All attendee lines are muted. If you have a question during the webinar, you can submit your question in the question box in the webinar panel on the right side of your screen. You can submit questions during the presentation. We'll do our best to get through all questions during the Q&A portion of our session. We are recording today's webinar for members unable to attend, and for any member who wishes to review the material later. Within the next few days, we'll also post the slides and recording to our website and YouTube channel. Now to introduce our guest. Tom Nugent is Chief Technology Officer and co-founder of PowerLight Technologies. He's been working in the field of optical wireless power, or popularly known as laser power beaming, for more than 14 years. His work has included system architecture design, trade studies, subsystem design, and component selection. That work has spanned all elements of power beaming systems, including lasers, high power optics, receiving, tracking, beam steering, photovoltaic power converters, power management and distribution, innovative active laser safety systems controls, and thermal management. Tom started his career working on advanced space propulsion concepts and hardware. He later worked at the Intellectual Ventures Labs, where he designed and prototyped medical devices, and also was involved in the photonic fence project that uses lasers to kill mosquitoes for malaria control. Tom is inventor and co-inventor of more than 60 issued U.S. patents, numerous foreign patents, and more than 12 pending patent applications. Tom, thank you for sharing your expertise with us. So at this time, I'm going to turn the webinar over to you.
Great. Thank you very much, Jorge, for the introduction. And as soon as I can share my screen, I will do so. There we go. And yeah, again, thank you for inviting me. It's great to be back with ETI to talk about power beaming. As Jorge said, my name is Tom Nugent. I'm the Chief Technology Officer and founder of PowerLight Technologies. And power beaming is a topic that's been getting more and more interest and awareness of its importance in the last few years. So let me start by just sort of answering the question is, who is PowerLight Technologies? We're a world leader in wireless power transfer and have been developing and making long-distance, high-power solutions that address sort of mission-critical needs for power in hard-to-reach areas. We've been developing this for more than 15 years now, and there have been a number of world firsts that we've done and different accomplishments over time in partnership with government, industry, and universities. We've been shifting from sort of R&D mode towards productization mode as our team has grown to nearly 30 people. There's been a lot of validation of the technology by third-party organizations and partners, starting with NASA in a competition we won, then with groups like Lockheed Martin, Ericsson, Intel, Airbus, and more recently with a number of groups within the DoD, including the Office of Naval Research, the Operational Energy Capabilities Improvement Fund, DARPA, as well as others. And one thing that repeatedly people sort of say they hadn't realized is how far along power beaming is. These are photos of some of the hardware demonstrations we've done over the years, setting different kinds of records along the way. On the left here is photos from that NASA competition. It was a technology competition that we won, brought home some prize money to start the company in earnest, and have done demonstrations with drones and other devices, indoors, outdoors, in some light rain, in the desert, day and night, in a variety of conditions, delivering sort of useful amounts of power over relevant distances. And as our technology has advanced, been doing it safely without requiring protective eyewear for people nearby. I'll touch briefly on power over fiber, which shares a lot of the same architecture and components as free space power, but sends the light through an optical fiber instead. And this can be useful to go underwater or into other environments where you're already running a optical data cable, but for whatever reason may not want to also run a copper wire. So to address the question of why people should care about laser power beaming, I want to take a step back and talk more broadly about energy. And one thing that some people sort of blur the lines on are these three different aspects of energy. There's the generation of the energy, electrical energy, with solar panels, with power plants, windmills, things like that. You can store electrical energy in batteries and capacitors, and you can store a different kind of energy in gasoline or in hydrogen. And then you can take that electrical energy and distribute it through cables and wires, or by carrying batteries to different locations. And I like to think about this as an analogy to water, where if you're pumping water out of a well, that's sort of your generation. You can pump it into a bucket or a tank and store it, but then you can send it through pipes to where it's needed, or you can carry that bucket to pour into a pot as you need to distribute it and use it. And so it's this, this issue of movement that's the broader question about how flexible is your power delivery and what do you have to move in order to get the energy there. If we start with a generator, for example, that you have a device that you can't just plug into the wall, it's going to be more remote. You could have a small generator near it, but now you have to have someone delivering fuel from the fuel depot and going back and forth and back and forth. And there's this repeated need to move mass to get that energy. You can have batteries that go into the device, but again, you need someone to charge those batteries, carry them, put them into the device, swap out the old ones, and go back and forth. And these kind of repeated motions of mass between the two ends can be asynchronous, which means the timing of the energy usage can be different from when the energy is generated. And these devices can generally be mobile. Now, you could have just a one-time movement of matter where you run an electric wire or, as I mentioned, an optical fiber for power. And so that's a one time, but now the devices are tethered. And so they're generally fixed and can't move around much. But now you sort of have an instantaneous reaction. So you have synchronous energy generation and consumption. When you turn up the volume on your radio, that extra power consumption is immediately pulled from the grid. And there are options where you never have to move any physical matter between your power source and the device that's consuming that power. One, you put a battery in a device and you send it off, and then you never go back to it. And whether it's a drone that falls out of the sky or a sensor that just stops reporting, it's one-time use. And of course, I'm here to talk about beamed power, where instead of sending mass, we're going to send light. We're going to beam the power from the source, whatever source it is, to a receiver that can then power whatever device needs to be powered. And there are a lot of different markets and applications that need more flexibility than traditionally we get from the electrical power grid. These are often located beyond the edge of the grid, either horizontally or vertically, and they can be in hard to reach or environmentally sensitive areas. And there's often an issue of the timing of how they can get energy out there. For 5G telecom, waiting for utility company to run a power line can cost money because it can take years. For the defense world, if you're, say, a Marine group landing on a beach and you want to set up a perimeter, having to trench cables to set up perimeter sensors takes time, whereas power beaming, you could very rapidly have those sensors powered and mobile. And so in all these different markets, they have a lot of common needs. And in what we call the age of wires, the cost and capacity of the wires is what sort of mattered for deciding how much power to install. But today there's this operational efficiency and availability that means we have to be able to provide the power needed to the remote target when it needs it. And a lot of these different applications have issues like the speed of deployment I mentioned, with issues of getting permits or being able to deploy wires for a temporary perimeter. There are many situations where it's impractical to install power wires. Clearly, a fixed wing aircraft, it's not really practical to run a power line to it, but also going across a river can be a temporary blockage to installing power wires. There is flexibility of placement of your device. Today, sensors and communication devices are placed where it's easy to get the power, where someone can access the device to recharge or refuel it. But it would be even better if those devices could be placed where they can have the best signal or the best ability to do their mission and not have to worry about running a wire to them. As I mentioned, carrying fuel and batteries back and forth costs people time, which costs money. And it would be better for warfighter, especially, to be doing higher value missions than swapping batteries. As I mentioned, there's cases where the environmental impact is a consideration. For example, if you need a cell phone tower on top of a hill, you might have to today cut down a swath of trees to be able to run a power line up to that tower. Whereas with power beaming, you may be able to get around that. There are some niche applications that require complete electrical isolation or require not doing high voltage that you would have to do in other cases. There's a lot of sensitive sensors that you don't want a wire to be an antenna or add noise to the system. But there's also situations, including underwater, where you can't have high voltage lines around people. And then, of course, out in the field, the warfighter could be exposed to enemy hazards if they have to leave a protected area to retrieve a drone to change its battery, for example. So all these different applications, whether it's telecom to rapidly deploy 5G radios that are much more densely located to each other than previous cell phone radios, drones to fly, getting power quickly after a natural disaster, as well as applications in the stratosphere and in space. These all have a strong need for flexibility in how they get their power. So let me give a brief background on how it works. So as I mentioned, we take electricity from someplace where it's easy to get, and we convert it into light with a laser. That light is shaped with some optics to project it a long distance to the receiver device. But that laser needs to have its temperature managed because it can't get too hot. And there's controls that steer the beam and that handle the safety that I'll talk about more as we get into this. On the receiver side, there are different optics that take that light and concentrate it onto photovoltaic cells, which are specialized solar cells, convert that light back into electricity. And that electricity can then be regulated, partially with these controls, to a form that's needed at the output where it can charge a battery or run a device. But of course, these PV cells, we have to manage their temperature as well. And then sort of wrapped all around this is a safety system that detects any objects approaching the power beam and then shuts the light off before anything can be exposed to it. And again, we're sort of agnostic to the type of input power and what kind of output power we need to deliver. So it's very flexible. For people who are coming from a radio background, the near infrared light that is generally used for the lasers is in the hundreds of thousands of gigahertz to give a sense of how separated the spectrum is from microwaves and radio types of devices. As I mentioned, power over fiber is very similar to free space power architecturally and with a lot of the components, except you don't need to steer the beam, and the light is now going through an optical fiber cable. And so places where you're already running optical fiber for data, adding some fibers to that bundle for power now gives you that merging of data and power through that single connection, which can also be done in free space, but there's a lot of that happening now for fiber. So to sort of understand some of the implications or limitations, I want to talk about the quality of light. And what I mean by quality of light in this case is radiance, which is sort of a measure of how well you can focus that light, excuse me, at long distance. And so sunlight gives us life, and it encompasses sort of all of the colors, all of the wavelengths of light. And all those waves are not in sync with each other. So they're out of phase, which means that light is not coherent. And so this means it has low radiance, low quality, and so it's very hard to focus it to a small spot at a long distance. Synthetic light sources like LED bulbs can use a narrower spectrum, a much smaller set of colors. The waves are generally not as much in phase still, and so it can be hard to focus, but you can still focus these tighter than you might sunlight. And then we can, of course, talk about lasers where you have a single color, single wavelength, and those waves are generally in sync with each other, in phase, which means that the light is coherent. And so now this higher quality, higher radiance light is much easier to focus at a long distance. So let me talk briefly about how lasers work. Inside that laser, we have what's called a lasing material, and there's some mirrors. One mirror is only partially reflective to let some of the light through. And so what we do is we pump energy in, and for a lot of lasers, that's electrical current. And as that energy goes through the system, an electron in some atom will be excited to a higher energy level. After a little while, it will relax and fall back down to the lower energy level and release a photon. Now, as those photons start bouncing back and forth in this cavity, the next time the electron is at this higher energy level, it can be stimulated to relax as a photon goes by. And so when that relaxation is induced, now the photon that it emits is in phase with that incident photon. And this is how you sort of build up the high quality light that's all in phase with each other. And one of the big trade-offs for power beaming system is how big is your transmit, your TX aperture, the size of your optic, and how big is the beam at the receiving end. I'm going to talk at an example here where we're going to take a kilowatt of light from different types of sources. And if you imagine a 10 centimeter optic, which is about 4 inches in diameters, we're going to try and focus that light to the smallest possible size at 1 kilometer. And whether we're talking about sunlight or different lasers has a huge impact on how big or small that beam can be. So if we take sunlight from a large area, get a kilowatt, focus it down into this 4 inch, 10 centimeter optic, and then focus it at a kilometer, the smallest we could possibly get in a vacuum, you ignore air for right now, would be the size of a football field. It would be end zone to end zone, a very large beam. But if we now take a bunch of laser pointers and again, get the same power, focus the same optic, go to a kilometer, now that beam size is an order of magnitude smaller. It's about a volleyball net. And so that is an improvement. But now if we start talking about high power diode laser arrays, and these are used in some materials processing and also heating of materials. And that is now a better beam quality. And now we're down to about the size of a yardstick, again, at this 1 kilometer distance. If we keep going to the next step up in beam quality or fiber lasers, and now that beam can be as small as a baseball at a kilometer. And these fiber lasers are used in industrial welding and cutting. And to get sort of the best beam quality, the highest possible radiance, we go to what's called single mode lasers. Fiber lasers are made in single mode as well. And these are again used in materials processing and also in directed energy weapons. And now again, with that 10 centimeter optic going a kilometer without air, you could get a beam as small as half a penny across. And so this is 4 orders of magnitude, a factor of 10,000 difference in diameter, which means it's a 8 orders of magnitude or 100 million difference in area. And so that is why we talk about beam quality and the types of light sources, because it affects the size of your apertures and how far you can go. On the receiving end, we have photovoltaic cells, and these sort of work like lasers in reverse, in that you have a semiconductor material, and it's made such that there's an electric field gradient. And now when you have a photon come in, it'll hit an electron and knock that electron loose from its place in the crystal. And this field gradient makes that electron migrate towards one side. The place where the electron was is called a hole, and it sort of has an effective opposite charge, and it goes in the opposite direction. And then at the surface of the semiconductor material, you have your electrical connections, and now your electron will flow through and complete the circuit, and that's how you get the electrical energy out of photovoltaic cells. This is a photo of one of the laser photovoltaic cells, and it's about 1 centimeter across, which is less than half an inch across. And this is a similar cell that's packaged in a carrier to make it easier to handle. And not only do we make the laser photovoltaic cells tailored to the wavelength of laser light, but because the intensity is so much higher, they are designed to be able to handle this intensity that can be 500 times or more as intense as sunlight. One other bit of context, again, getting back to radio waves and the whole spectrum. If you have one of these charging pads for your phone, it's usually the Qi standard. These sort of near field charging solutions have a very long wavelength, low frequency, and they sort of overlap where the radio spectrum is. There is a way of delivering power wirelessly with microwaves or millimeter waves. This is in sort of the gigahertz range and overlaps with Wi-Fi and where your cell phone operates and how your microwave oven regulates. And this wide spectrum here is regulated by the FCC. They have very strict controls on emitted radiation. As we keep going to higher and higher frequencies, which means shorter and shorter wavelengths, we get into the infrared. And so you as a person radiate infrared light in sort of this general range. As things get hotter to what you might call red hot, like with a metal, now this spectrum shifts to the right, closer to the visible. Just before you get to the visible is what we call the near infrared, which is generally not what's used to see in thermal cameras, but it is where, say, your TV remote operates. It's what's used for all of the telecommunication optical fiber data exchange. And lasers exist across sort of the visible, even into the ultraviolet, but specifically in the near infrared for power beaming and other applications. People often ask about directed energy weapons, and there is a lot of similarity in the technology, and much of it is compatible, but the requirements for directed energy weapons is generally overkill compared to what power beaming needs. And so there's a laser, as I mentioned, they definitely want the highest quality beam to be able to focus at a small size. They want to make that beam shaped so that it can be as tiny as possible, to make that beam as high intensity as possible to get their effect on their target. The target for a weapon is hostile, whereas for power beaming, our receiver can have a beacon saying, hey, here I am. And so that makes the tracking of that much easier. And the DE weapons might need to react to an incoming mortar, whereas power beaming does not have that urgency. And so things like how you turn the beam director is much more relaxed. So all of this means that the requirements for a power beaming laser system is easier and lower cost. And I sort of make the analogy between a pickup truck and an 18-wheeler big rig. The directed energy weapon is the 18-wheeler, and you can do a lot of big stuff with it. But if you just need to get groceries, go to Home Depot or whatever, your pickup truck is going to be just fine. But it's important to note that a lot of the current directed energy weapons operate in the similar wavelengths that we're using for power beaming. And so receivers can be compatible with directed energy weapons. And in fact, just wrapped up a program that was demonstrating a receiver tailored to the burst nature of laser weapons. And so this gets to a bit of a nomenclature confusion when we talk dual use. There was a program called Dual, and that was aimed at making directed energy weapons have a second function. Their primary mission, of course, being counter UAS or counter mortar functions. But in the 99.99% of the time they're not doing that, they can have a second use to deliver energy. But power beaming is itself sort of agnostic to use, just like an extension cord can be used in any context. Power beaming, of course, has both commercial and defense applications. So why are you hearing about this today as opposed to a decade ago or a decade from now? And there's a few reasons for that. One is that the components, the big components, lasers and photovoltaics, have been getting better performance and lower cost, excuse me, for decades now. Lasers have their own Moore's law like progression where the price per watt of power out falls in half faster than every 3 years. And all signs point to this continuing into the foreseeable future. Photovoltaic cells have, of course, fallen a lot in price over the last couple decades. And the laser photovoltaics are a variation on that. And so they get heritage, in fact, from the concentrated photovoltaic cells that were popular a decade or so ago, and use a lot of the same semiconductor processing equipment. So these prices of these expensive components is falling so fast that the economics is making it more realistic. Another reason is that there's sort of growing interest and issues around international competition. As we're all sort of aware of, there's a long history of various technologies being developed in the United States and then moving overseas. And relevant to power beaming, lasers and photovoltaic market is dominated currently by China. Today, the United States leads the world in developing power beaming technology. And a lot of that has been with the support of the Department of Defense and work done by PowerLight, especially, and also some other groups on extending this distance power, working on safety and other aspects, and getting it outside of the lab. But there are programs in Japan, China, Europe, and probably elsewhere developing power beaming capability. So we'd like to stay ahead of that as much as we can. So now that we've sort of talked about how it works, let's talk about what it can do for you beyond just saying you can go wirelessly. The power you need and the distance you need to deliver that are sort of main criteria. And as I mentioned, there's been a wide variety of different groups, industry, government, universities, demonstrating power delivery, both via laser and microwave. And to give a sense of the scale, at the bottom we have some icons here, a person sort of across the room distances, all the way up to, a mile, as tall as Everest is, or even running a marathon out here. And the power levels from a light bulb up to your microwave oven or even your EV car. And as you start looking at the higher powers, longer distances, there's not as much activity. A lot of the demonstrations have actually been PowerLight, the PLT here. And the one milestone that we still have to break, or somebody has to break, is back in 1975, NASA JPL, the Goldstone antenna, used a 100-foot antenna dish to send 34 kilowatts of microwave power almost a mile to receivers. So we focus in on this sort of higher power area. For us, there's this nice sweet spot or overlap between three large markets, defense, telecom, and space, especially on the moon, where they need this kilowatt class power at kilometer scale distances, whether it's for radios, sensors, drones, rovers, and craters, whether it's hundreds of watts or a few thousand watts, half a kilometer or 3 kilometers, there's a lot of overlap here. And this enables us to be developing products that can easily be adapted to those different markets. A power beaming system, even though we sort of say it's just like an extension cord, is very complicated. And I've mentioned sort of the laser and the photovoltaic array, but there are many different factors that impact the electrical efficiency. But electrical efficiency, as I've talked about before, isn't the whole story. When you have to carry batteries or do installations, there are other factors that get into the operational efficiency of the power beaming. And so if we sort of summarize a little bit, different alternatives to plugging into the grid exist. Sunlight is free and has been falling in price, but it can be very large for a certain amount of power. Generators are widely available, long heritage, but they're noisy and need maintenance. And again, you have to get the fuel there. Batteries are silent, rechargeable. They're ubiquitous, but they have their lifetime limits, and you have to usually turn off a device when you're taking the battery out of it. Microwave power beaming can get through clouds and rain much better than laser light, but it is in that spectrum regulated by the FCC and internationally the ITU, and is very large. Its radiance, when I was talking about beam quality, is closer to sunlight than it is to lasers, and this possibility of RF interference. Each of these has their own places where they shine or are most relevant. Power beaming will have part of that use case where we have simpler regulatory issues. The FDA regulates laser products and a self-certification. And by always monitoring how much we are powering the laser and getting data out of the receiver, we're always sort of capturing data about how much power is being delivered when. So let me talk about drones. And the sort of biggest factors for drones is what payload they're carrying. You want to always carry more of a payload and fly for as long as possible. Combustion engines have a high power to weight ratio, or what we call specific power. They can deliver a lot of power in a small amount of weight, but eventually you run out of gasoline. And so the amount of energy per unit weight is limited by gasoline. Fuel cells are in some senses similar to gasoline. It's just got hydrogen fuel and after in a different condition, but eventually you run out of that hydrogen. Batteries can discharge very rapidly and get very high power to weight ratios. But again, the electrons eventually are all used up. There has been advances in the last 15 years since we started in terms of how much energy you can pack into one battery. And so it's advanced, but it's still on this scale relatively small, and battery advances are relatively slow. Some drones go the solar electric route, where they cover the entire top of the wing in solar panels and then have batteries to get them through the night. Because of how diffuse sunlight is and the fact that it's not there all the time and they need these heavy batteries, their power to weight ratio is relatively low. And so these solar electric vehicles are generally very limited on payload, but they can fly maybe indefinitely because of the day-night cycle. Batteries have a lifetime, and so they probably can't fly forever because the battery eventually wears out. Optical power delivery gets sort of the best of both worlds. It's been demonstrated to have this high power to weight ratio, and because you can fly continually on the beam, you may be able to go long periods of time without even having to really touch the battery. And beyond the power to weight ratio, if we continue and then look at area, this graph, the vertical is the same power to weight ratio, but now horizontally, we're sort of looking at the power per area. How big is the device that's giving you that energy? And if we sort of look at solar arrays or wind power, they have a very low, averaged over 24/7 output power per unit area, the footprint that they take up. Nuclear or oil power plants have much higher power per area, and so they can take up less space. But the demonstrations that we've done with different power beaming systems show a very high power per area metric. And if we're really comparing these to solar panels, it's a factor of 1,000, 3 orders of magnitude more, which means your area is a factor of 1,000 or more smaller. And there's no physics to say that we can't go even higher. And so as this technology matures, we expect that power per area to go even higher. And that means that you'll be able to get a lot of energy from a small footprint. As that footprint gets smaller and smaller, that implies that the beam is getting more and more intense. And the one factor that means is that there's laser safety issues to consider. The sunlight is sort of, you can't stare at the sun because that will very quickly burn your retina. And lasers are more intense. And to get the usefulness out of power beaming, where you're going to get it in a small area, you are in this threshold where it can be an eye hazard. Now, we're not talking intensities that's going to cut or burn anything. It's sort of potentially damaging to your skin or your retina. And the way we deal with that is by having active safety sensors that can detect objects approaching the power beam, so it can be turned off temporarily while the object, sort of goes past, and then the beam can be turned on. And because of the importance of safety and needing it to be as safe as an extension cord, Powerlight has been developing various sensing technologies for safety. But it's not just enough to turn off the beam anytime you detect something. You want to be able to turn it off for people and birds, but you don't want to have to turn it off if there's a leaf falling through or if there's raindrops coming. And so some of the work on these safety sensors is to differentiate between different types of objects. Of course, there's going to be some jerk who's going to try and take a mirror and throw it through the beam. So we have to be able to detect that and keep that light from escaping this protected area. One thing we've started more recently is what's called a LOPA analysis, which is layers of protection analysis, that follows sort of standards for functional safety to even more accurately quantify all the different types of hazards and how safety sensors can mitigate those hazards. As mentioned, we've demonstrated this with one safety system, our light curtain, that from when an object passes the sensing point to when the laser was off is as fast as a millisecond, which gives a lot of flexibility in allowing people and other objects very close to that laser beam without needing any protective eyewear. This technology is optically based, and we've been able to get it to work even, as you can see here, near asphalt in the summer, a lot of scintillation, still able to get a good signal to be able to detect objects and shut off the laser in time. So what is coming up in the future? To start with, the technology is continuing to get better. I've talked about the photovoltaic cells and the lasers. They're both getting more efficient, and there's reason to believe that these laser photovoltaic cells will be able to get more efficient, because this black line here is sort of how close solar cells have been able to get to theory, which is the blue line. And for one laser wavelength, these PV cells have already been approaching that practical limit. And the wavelengths of most interest to us today have room to grow. Lasers are, of course, being driven by the industrial processing needs to get more efficient, to get better beam quality. But then, we and others are working on designs to make the overall system designed to be more efficient, to scale up to deliver more power, to be able to properly and safely reach longer distances. And of course, develop this into a product that can go into the field. On that point of efficiency, one thing to note is that as the efficiency increases, and this is sort of part of our roadmap for how to increase that efficiency over the next 5 to 7 years, the returns to how much input power you need to provide get to pass the knee of the curve and into the diminishing returns. So if you go from 10% to 15% efficiency, the drop in the input power required is much bigger than when you go from, say, 30 to 35% efficiency, the drop in power is much more modest. We are pushing and believe that we can get above that 30% point in the next 5 years or so with adequate funding. And that comes from sort of two different sources. This blue is what the lasers and photovoltaic cells lose, and the orange is everything else, your chillers, your controls, other aspects of design where you might lose light or electric power somewhere. And all of that is increasing in tandem to make the systems more and more efficient. So, we and DARPA and other groups have this vision of a network of wireless power, where you can not only beam, say, from ground to air or space to ground through the ocean, but that you can even have relays that take light and just redirect it to go even further distances. And now you can imagine networking power sort of in packets like you do for data over a data network. And that's going to just dramatically expand the possibilities for where devices can operate. So imagine that you have drones that never need to land, or they can fly for a year. And the Assistant Secretary of Defense Chris Lohman had made a point that because we currently lack effective power distribution options in the DoD, the power generation and storage devices are over-engineered, which makes them much less efficient and introduces risks to the system. Power beaming allows you to distribute that and be more efficient in how you're managing your overall energy and operational budget. So to this point, we have started working on a program to get a field test ready system for power beaming to a Group 2 UAV. And we've been getting some support from the Department of Defense now. This program is called Power Transmitted over Laser to UAS. And the target is to send power to this drone at altitudes up to 5,000 feet. And as long as there's no clouds, and it can fly low or below clouds if necessary, be able to power it 24/7, day, night, any time of year. And this will not only enable, say, a couple of drones to, say, swap places. The fast recharge means that you're actually even saving time potentially in the recharge, where landing, servicing the vehicle as it gets roughed up when it lands and things is actually quicker than having the people do that. You can just beam the power. And the missions for drones depend on their payloads, and those payloads, you can now imagine having higher power payloads, because this providing of energy from the ground really opens up the envelope of your energy budget. And so now, we're sort of imagining what happens if you can make autonomous systems actually autonomous, where they don't have to come back and have a person swap out their battery, but now they can operate indefinitely with this autonomous power system to be able to keep operating for months without needing any human intervention. And imagine after natural disasters, where it can be very hard to get generators or other supplies into, like gasoline, into affected areas, you could beam power in immediately to set up communications and field hospitals. The US Navy has a humanitarian mission, and after Haiti, the earthquake in Haiti 12 or so years ago, and after the Fukushima incident in Japan, naval vessels were there right off the coast. And if they had power beaming, they would have been able to much more quickly get power into places that needed it. And as we go to the moon, the permanently shadowed craters are of interest, but with no sunlight, it's very challenging for rovers to operate out there. And whether you have rovers or people, extended periods on the moon have up to 2 weeks of nighttime, and the cold and lack of sunlight is challenging. But beaming power from orbit to those devices really expands, again, the possibilities for operations on the moon as well as in space. So with that, I just want to end by saying that laser power beaming is much closer to reality than a lot of people think. It's been shown to be safe. We've shown over 15 years that you can get kilowatt kinds of power at kilometer kinds of distances, and it's ready for prime time. If you are interested in learning more in the technical side, I am co-author on a book that came out earlier this summer on power beaming, where we talk about both microwave and laser power beaming and do apples to apples comparisons and dive more deeply into the technology. So with that, I want to thank you very much for your time and attention, and I'd be happy to take any questions.
Thanks, Todd, for that great presentation. We're going to roll into question and answer period. So the first question that I have is from Mickey Wright. And the question is any of this power beaming in use today? Is it are devices out there in the commercial or military operations?
So there are none in military use, as far as I'm aware. There are the Qi, or these inductive chargers where you have to get almost touching it, that I think has maybe been deployed, or it's certainly been getting further along in the military. On the commercial side, there are a couple of companies doing either microwave or lasers for very low power, like less than a watt of power over short distances, like across a room. And they're powering devices like Internet of Things kind of sensors, very low power. But there's nothing yet out in the field, to my knowledge, for the military.
the next question comes from Sam Moyer. How does the efficiency of power beam devices compare with wired or transmission approaches? I guess we're talking about how you're trying to reach that 30%, but are there other technologies that have already reached that, and what's the comparison?
So there was a demonstration back in the 1970s on microwaves in a lab where they got complete end-to-end efficiencies of 50%. Today, the components for microwave power beaming can be more efficient, but because the apertures have to be so big, they usually just don't make them quite as big, and a lot of the energy is just sort of spilled past the receiver, and so it's wasted. So microwave systems today, in theory, could be more efficient, but generally they're not because of that wasted energy. If you're talking about things beyond power beaming, wires are not actually 100% efficient. Your high voltage power distribution lines going from city to city are at best maybe 90% and probably less. In the telecom space where they're trying to get power to these radios, those, when they use wires, are only 60 or 70% efficient. And so when we get up to 30% efficient, now you're sort of already half as good as some of the existing wired solutions. So power beaming is not going to replace distributing all of the energy for the grid. It's really for places where you need to go beyond the grid, where the sort of excess losses beyond what you get from wires is more than worth it because of the other advantages.
You're talking about like going off grid. I have another question from Richard Campbell, and his question is, are relay stations needed for like long distances?
Yes, and for sort of two reasons. One, especially if you're on the moon, the horizon is relatively close, and so to get sort of over the curvature of the moon or the Earth, you need relays to keep that line of sight. But on Earth, the atmosphere low down to the ground is very dense, and so there's dust and other things that will absorb and scatter the light. So this DARPA power program is looking to overcome that by beaming from the ground up to a vehicle in the stratosphere, which then relays the light potentially hundreds of kilometers horizontally, where the air is so thin that you have very little loss. And now you can get down hundreds of kilometers because you've been relaying that light where the air is thinner.
So you talked about demos using for the upcoming demo or field testing of for the powering a UAS. You talked about the work with DARPA as far as beaming power up into space. Are there any other demonstrations out there that are happening or will happen in the near future?
I believe that Lockheed Martin had announced a demonstration at a conference earlier this year. I haven't seen the paper yet. As I mentioned, there's these sort of short-range commercial devices that are for sale for homes and grocery stores. I'm not sure there's a single place to sort of look and see whether demonstrations are coming up. The power program, its first phase is, I believe, ending in the spring and moving on to a second phase where there'll be a demonstration a year or two after that. But if people have questions about specific demonstrations, they're feel free to reach out to me, and I can probably give a better answer offline.
Now, you're talking about how you're using power beaming and the safety concerns about that, and how you're designing these systems to be able to detect something coming real close. So Jim Lent has a question. Would the power beam be detected by enemy forces? I guess that's kind of one of those design things that would need to be considered,
Right.
as far as power beaming devices, because you can imagine an enemy saying, well, if I know I can shut the thing down, I'll just throw something at the beam and shut it off, right? Or
Right.
another question someone had was, what is the probability of detection of the beam? Can you see it, beyond the beam, or you can only see it if you're in line with the beam?
Right. So the short answer is it's complicated, and there hasn't been enough research done on that yet. The near infrared spectrum is invisible to people, but it can be detected by certain kinds of sensors. The wavelengths we're shifting to are sort of mostly beyond what your standard silicon sensors can detect, but those longer wave sensors are becoming more ubiquitous. So at the transmitter and at the receiver, there'll be a little bit of scattered light, and you can talk about baffles and things to reduce their visibility. The beam, most of the scattering that happens in sort of a forward direction. So from the side, you may not be able to see it very easily, whereas if you're sort of closer to in line, sort of behind the receiver looking towards the transmitter, you would have a better chance of detecting it. Now, that's at night. When we use IR viewers to see the beam, at daytime, it's really hard to see. And so in cases where you really need to be not detectable at all, there are games to play around when you're delivering that energy, and what you can do with making it so that it's harder to tell where the devices are by choosing when and how you deliver the power.
So can you just review, I think you've talked about this, but can you review just the constraints or the challenges of using power beaming, whether commercial or a military application?
So on the regulatory side, as I mentioned, it's laser products are regulated by the FDA, along with lasers for laser light shows, X-ray machines, and lasers for like eye surgery and stuff. It's a self-certification process, and so it's a relatively straightforward process. So there's that one. We sort of look beyond the regulations to making the system safe, so that an insurance company will, treat this like any other sort of UL certified device as being safe. The prices of the components have been coming down, but they're still not cheap. And so as we start getting these systems going, we have projections that we made for the telecom world. As it scales up, it eventually becoming price competitive with copper wires when you include things like the cost of the people and other things for installing the power lines. But that's once you get to a very large scale. As you mentioned, lasers are line of sight. So if you can see the other end with your eye or with a telescope, you can get power there. If you have precipitation, just as you can't see quite as well when there's some rain, the efficiency might go down, or your maximum distance might come in closer. But rainfall, you usually don't have very heavy rainfall for very long. And so again, because we usually have energy storage in the form of a battery at the receiver, you can keep operating your device when the laser shuts off for 15 minutes of heavy rain, or for 5 seconds of a bird flying through. And so being aware of what all those constraints and requirements are allows us to sort of size the system so that it can handle those interruptions.
Yeah, I guess in this case, size definitely has is a factor in all these things. When I have another question here from Anna Kim, do you expect power beaming infrastructure is more resilient or survivable than traditional energy infrastructure? For example, would power beaming receivers be expected to survive a natural disaster that might damage traditional type of grids?
Potentially, at least in some situations. So for example, if I have a large solar array to give a certain amount of power, that's just so large that you're more likely to have something fall on it or have it break in half. Whereas if my laser power beaming receiver is much, much smaller, then sort of the statistical chance of it being hit by something is less. It's not so big that it's going to have sort of flexure issues as you would with a giant panel. Without having those wires between them, you don't have to worry about the wires being cut by, again, a falling tree or something like that. So, you know, where you're getting your energy from, if the laser is powered by the grid and the grid is down, that doesn't help you. But for at least some aspects of natural disasters, even if it's already there, the power beaming can be more robust than traditional infrastructure. But because it's small, it's also easier to quickly get in place, even if it's not there already.
Okay, Tom, I think this is at the end of our time here. And I want to thank you for taking the time to enlighten us about power beaming. And hopefully we can talk again some future ETI Tech 101 and tell us more about developments and things that are happening in the near future.
It'll be my pleasure, and thank you for the opportunity.
You're welcome. And also thank you to the audience for those great questions. We'll post the recording online as soon as possible. You know, that was one of the few questions that came up about the availability of the recording and the slides. If you have any feedback about this event, especially topics that you'd like to see us cover in the future, please email us at ATI. The address is eti@ndia.org. That's eti@ndia.org. I also want to take this opportunity to highlight a few of the ETI upcoming events. I think the slide will come up here. The first event would be the Women in Defense Conference that's occurring in Arlington, Virginia, on September 24th. The next conference is the Future Forces Capabilities Conference, and that's happening at Virginia Beach Convention Center between September 24th through the 27th. Our next ETI Tech 101 will be in October, and it will cover extended reality technologies. So be on the lookout at the NDIA's website calendar of events for more information. Leveraging artificial intelligence for acquisition symposium in partnership with MITRE is going to happen in October 18th between 8 and 4 in McLean, Virginia. And to register for any of these and other ETI events, please visit our NDIA events website, which is www.ndia.org/events. That's www.ndia.org/events. Thank you for joining us today.